Welcome to Chemistry for Non-Chemists. This episode is about dissolving stuff. As we discussed last time, electronegative elements love electrons. But what if the molecule has a mix of atoms with high and low electronegativity, like oxygen and a couple of hydrogens, which is water? We see that oxygen has 3.44 electronegativity, while hydrogen has 2.2. This results in a molecule that looks like a magnet. The oxygen side is a little more negative, we say it's partially negative, and the hydrogen side is a little more positive, we say it's partially positive. Since there are two poles, we say that this molecule is polar because it forms a dipole, di meaning two. Same as a regular magnet that also has south and north pole, and therefore forms a dipole as well. What happens when we put two magnets together? The positive side of one attracts the negative side of the other. And the same effect happens here. The molecules of water will align their opposing sides. This forms attraction between them, known as intermolecular forces. Inter meaning between, as opposed to intramolecular, which are the forces within the molecule. Due to these intermolecular forces, the water molecules tend to stick together, which, for instance, is a reason why water forms drops. Here's a rule. Polar molecules dissolve other polar molecules or charged particles, meaning ions. For example, water can dissolve salt. Why? Remember that salt crystal is held via ionic bonds? But inside the crystal, sodium is a positive ion and chlorine is a negative ion. So negative parts of water will be attracted to sodium and will be able to detach it from the crystal. And partially positive sides of water will be attracted to chlorine and will do the same with it as well. The water molecules then surround each of the ions, and this way they keep them suspended. And this is a dissolution. So water can dissolve salt. And dissolving means that molecules of solvent, in this case water, attract molecules or atoms of whatever we're dissolving, in this case salt, and they all become intermixed. So the solvent and the solute don't form separate layers, they mix together. And by the way, remember that the human body is mostly water? What do you think happens to all the salt that we eat? It gets dissolved in the blood, inside the cells, and in the liquid between the cells. Your body contains lots of sodium and chlorine ions floating around, and they have important function. They enable neurons to send the signals and muscle cells to contract. Other ions, like for instance potassium and calcium, participate in these processes too. And that's because they give some of their electrons and become charged particles, ions. And that in turn allows them to be dissolved and carried by the bodily fluids like blood. Now, what if the atoms within molecules have more or less the same electronegativity, like carbon and hydrogen? Carbon has 2.55 electronegativity versus 2.2 of hydrogen, so more or less the same. Then the molecule is called nonpolar. Such molecules tend to form weaker intermolecular forces. But why do they have any attraction at all? Since atoms and molecules are dynamic systems, the electrons can move slightly back and forth. And when they are slightly to the one side of the molecule, it makes the other side of the molecule a little more positive, which attracts the electrons from the other neighboring molecule, which makes the other side positive as well. But when the original electrons move back, the attraction disappears. Such forces are called London Dispersion Forces, and London is last name, not the city. And here is a rule. Nonpolar compounds, like benzene, tend to dissolve other nonpolar compounds. However, if you mix benzene and water, they don't mix. Benzene forms a film on top of water. This is the sign that the molecules don't dissolve each other. But why? Well, imagine you put two magnets close to each other. There is some air between them, but they won't care. They're going to push the air particles out of their way in order to meet. And something similar happens to water molecules. They're going to push out all the nonpolar molecules. They will meet. And they will form a separate layer. And then the nonpolar molecules won't have any other choice but to form a separate layer too. And so this brings us to the last rule. Polar and nonpolar molecules don't mix, and therefore they cannot dissolve each other. Polarity, however, is not a binary property. Some molecules can be a little more or a little less polar, It depends on the proportions of the polar parts compared to the size of the molecule. If we see that there are very few electronegative elements, like these two oxygens, then it's probably not very polar. By the way, we're looking at a lipid. Lipids are compounds like oils, fats, waxes, etc., and they consist of nonpolar tails, which are usually quite long, and polar heads, which comprise of different stuff. This molecule is still nonpolar, as this head is too small to make a big difference. And you probably know this from your experience dealing with butter. For example, it's hard to wash it away, and that's because polar water doesn't want to interact with nonpolar fat. But not all lipids are like that. Some of them have large, very polar heads, allowing them to dissolve in water too. Since fat and oil molecules are long, what would happen if they align nicely? Yes, London Dispersion Forces are weak, but they're going to be happening across this whole long sausage. And a lot of small forces can add up to a rather strong interaction. The better the alignment, the stronger the interaction. And we can draw some rules here too. If molecules are rather straight, they can align and form stronger bonds. Like butter, it's hard at room temperature because its molecules are quite straight. If on the other hand, the molecules bend like this, the intermolecular forces are weaker because they cannot align nicely. You can imagine some of the molecules will spoon each other, but others will be located differently, and the interaction is going to be around a much smaller area. And these are oils, which are liquid at room temperature. And by the way, if every carbon has a maximum number of hydrogen, such fat is called saturated. Like this, every carbon is surrounded by 4 different atoms. Now here, we see a double bond between 2 carbons. Here it is. It means that at this position, because there are only 4 bonds that the carbon can form, these 2 will be surrounded only by 3 elements. And these are called unsaturated fats. As usually, there are nuances. We already know that the interaction between molecules depends not only on polarity, but on the size and the shape. Also, some molecules are both polar and nonpolar depending on which part you look at. This makes it harder to reason about which compounds dissolve which just by mentioning their polarity. This brings us to another terminology that describes this directly. Compounds that are dissolved in water are called hydrophilic, meaning water-loving. Those that don't are called hydrophobic, meaning water-fearing. Compounds that like lipids are called lipophilic, and those that don't are called lipophobic, though this one I've never heard used in real life. Somehow it seems like scientists can hate lipids. I mean, look at this guy, am I right? Now, hydro and lipophilicity aren't mutually exclusive. Here is soap. But wait a minute, isn't this just a lipid? And yes, it is, but notice that there is no hydrogen here. It was taken away, but it left its electron with oxygen, and that's why this oxygen is negatively charged. In order to balance the charge, we added a positively charged sodium. Hopefully you remember that this is called an ionic bond, and this is similar to sodium chloride or table salt from our previous video. And it's also a salt, just not a table salt. Remember what happened to the salt when it was placed in water? The water removed sodium from chlorine. It dissolved the salt, and by the similar mechanics, the water removes sodium when we use the soap. What's left is a lipid, but it's ionized. It's one thing to have electronegative elements making molecules polar, but an ion, an actual charge, that has a lot stronger effect. Water loves it. All in all, this allows the soap to be dissolved in nonpolar substances. It dips the lipophilic tail into the fat on our hands, while the hydrophilic part is pulled by the water. This makes soap good at washing away the fat from our hands, along with all those nasty bacteria and viruses that are stuck in it. Here are some other interesting molecules. Hydrophilic vitamins like vitamin B can be easily transported by the blood. Even if you eat too much of vitamin B, the blood can relatively quickly deliver it to the kidneys for further excretion. Well, that is, if the kidneys work well. Hydrophobic vitamins like vitamin D move through the body much harder because they don't dissolve in blood easily. They require a transport protein, meaning they get attached to another molecule that in turn is dissolvable in blood. But because it's lipophilic, it can also get dissolved in the body fat. So if we eat too much of it, our body can't necessarily excrete it quickly. Remember, a lot of it is in the fat, not in the blood, and its levels can reach toxic levels much faster, so it's easier to overdose with the vitamin D than with the vitamin B. By the way, if you watched House MD TV series, you may remember an episode with a boy that got exposed to some toxic compound, and as he was staying in the hospital, he was eating diet food and was losing weight. As he got less and less of fat, the toxins stored in it spread through the body and the boy got sicker and sicker. It's the same reason. The toxin was hydrophobic and therefore it stuck in the body fat instead of moving with the blood, and then got released in large quantities very quickly. Capsaicin is another interesting molecule. It's the component of pepper that makes it spicy. As you may already know, you cannot easily relieve the burning sensation with water. That's because this molecule is lipophilic, though it's harder to see because it has all these oxygens and nitrogen. So if I were to look at this molecule myself, I wouldn't necessarily say that it's lipophilic, but apparently it is. And it's much easier to dissolve it in lipids. And where do we have lipids? In milk, which is a typical advice to drink if you want to wash out the capsaicin. This is an interesting molecule. It's a so-called phospholipid. It's one of the lipids that comprise our cell membranes. As you see, it has a large hydrophobic tails and a large hydrophilic head, which means this part is soluble in fat and this part is soluble in water. And the way it looks is this. It forms two layers, and in both cases the lipophilic tails meet, and the hydrophobic heads, they meet water on the outside of the cell and on the inside of the cell, which forms a very stable structure naturally. And also it does not allow a lot of hydrophilic substances that are dissolved in the blood to go through the membrane, because this layer is lipophilic, and this forms a barrier because a lot of substances that are dissolved in the blood are lipophobic and they cannot be dissolved in this layer of lipids. Now, there are ways of measuring hydro and lipophilicity of the molecules. Take two solvents, one polar, like water, and one nonpolar, let's say octane. Put them together with a compound that you want to measure and shake it. At some point, the polar and nonpolar solvents will separate into layers, then measure how much of our compound of interest ended up in one layer versus the other. By taking the proportions, we measure so-called partitioning coefficient. We also take a logarithm, which chemists really like, and we get a logP. This property is one of the most important factors during drug discovery process, as it tells scientists how well the drug will be absorbed by the cells or distributed by the blood. Too hydrophobic and it won't cross the cell membrane and it will be excreted too quickly, and too lipophilic and the drug can be toxic. And it's a good stopping point. See you next time.